Question number 6. When heat is absorbed during a chemical reaction, the reaction is said to be endothermic reaction. Okay? When it is absorbed, the reaction is always endothermic. Okay? But if it is given out or released, we say that the reaction is exothermic. So that is endothermic and exothermic. Now let's look at the energy profile of the endothermic reaction. Okay, we have the energy up there, and we have the reaction pathway in the horizontal axis. That is the reactants, that is the product. Okay, the energy of the reactant is that is enthalpy of the reactants. The energy of the reactants, that is the enthalpy of the products as well. Okay, we can now see the change in energy, that is change in enthalpy, delta H is equal to the enthalpy of the product minus the enthalpy of the reactants. Okay, now the enthalpy itself, what is enthalpy? Enthalpy is the total heat of a system, or total energy of a system. That's what is called enthalpy. Okay, and the delta H, that is change in enthalpy, is equals to the enthalpy of the products. Can we see the enthalpy of the product there? Minus the enthalpy of the reactants. That's the change in enthalpy. And the enthalpy of product is more than the enthalpy of the reactant, as we are seeing there. So the delta H, change in enthalpy, will be greater than 0. That is, it is positive. Positive. Okay, so we also have what is called activation energy there. Activation energy is the minimum energy that is required for a reaction to take place. So up there also as well, we have what is called activation complex. Now we want to look at the energy profile of exothermic reaction. We have the energy at the vertical axis there, the reaction pathway at the horizontal axis. We have the reactants, and we can say we also have a product there. The energy of the reactants is HF. The enthalpy of the products, HP. The enthalpy of reactant is more than the enthalpy of the product. I think we can say it's there. Okay, now change in enthalpy is equals to the enthalpy of the product minus the enthalpy of the reactant, and since the enthalpy of the product is less than the enthalpy of reactants, so we should be able to have a negative, that is a number less than 0 rather, which will be negative. So delta H is negative for exothermic reaction, and these are delta H. Okay, is given there. Okay, and we also have what is called activation energy there. Okay, as I've said earlier on, activation energy. Okay, we have that as well. So up there we also have what is called activation complex. Okay, now let us look at some other things about exothermic reaction. In any exothermic reaction, number one, the products have less energy than the reactants because energy has been given out to the surroundings. That is, the change in enthalpy is less than zero. That is, it is negative. Number two, the bonds formed in the products are stronger than the bonds broken in the reactants. Number three, the reaction vessel becomes hot. Examples of exothermic reaction. Number one, the complete combustion of fuels. Number two, neutralization reaction, and so on and so forth. In any endothermic reaction, number one, the reactants have less energy than the products because energy has been absorbed from the surroundings, so change in enthalpy is positive. Number two, the bonds broken in the reactants are stronger than the bonds formed in the products. Number three, the reaction vessel becomes cool. Examples of endothermic reaction. Number one, the thermal decomposition of calcium carbonate. Number two, dissolving common salts, sodium chloride in water. It can even be ammonium chloride, and so on. Question number 7. Which of the following best represent solid gas mixture? Milk, kerosene, soil, smoke. The smoke is the answer. And the smoke is an homogeneous mixture of two phases. So, milk is also homogeneous mixture. Now we'll talk about them. They are colloids. Colloids, they are homogeneous mixture of two phases. The dispersed phase, which is the same thing as solutes of true solution, and dispersion medium, which is also like solvents. Examples of colloids will be given shortly. Colloidal dispersions. Dispersed phase, which is like a solute. Dispersion medium is like a solvent. We have a gas dissolved in gas. There's no example for that. We have a gas dissolved in liquid. The example is foam, leather. We have a gas dissolved in solid. Example is charcoal. We have a liquid dissolved in gas. The example is mist, cloud. We have a liquid dissolved in liquid, give you emulsion. We have a liquid dissolved in solid, give you paste, gel, and sol. We have a solid dissolved in gas, give you smoke. That's what we just did. We have a solid dissolved in liquid, give you milk. We have a solid dissolved in solid. We have good bearing rock. This is an example of colloids. Memorize them. Question number 8. Hydrogen ion plus hydroxide ion gives water. Hydrogen ion there can be said that to be an acid because an acid interacts with water to give hydrogen ion. Now if you look at the base also as well, a base interacts with water to give hydroxide ion. So we can say that that one is also a base. So it will now give us water. So we can say the reaction is like a neutralization reaction where an acid reacts with base to give you salt and water. But if it is hydrogen ion that is written and hydroxide ion, it will give you only water. It is still the same thing as neutralization reaction. Question number 9. Electrons enter into orbitals in order of increasing energy as exemplified by number A. Okay, when you have increasing energy, so we should be talking about what is called orbital principle. It's one of the principles that is used in writing electron in an orbital. Okay, so we have one S2 there, 2s2, and we have 2p4 there. Okay, for the s orbitals 1s2, it has one degenerate and maximum of 2 electrons. The same applicable to 2s orbital there. Now the p orbital has 3 degenerates and maximum of 6 electrons. Each degenerate will get 2 electrons. You can now see this is 2px2, meaning that you have 2 electrons in the px degenerate, 2 electrons in the py degenerate. Okay, having this, it is totally wrong because it is against one of the rules, which is called Orn's rule, which says that the electrons are filled into suborbital singly before you pair them. Now let's look at the second one there. We have 1s2, you have 2s2, you have 2p4 as well. But in this case, you can see 2px there, 1s2 there, 2 electrons in the degenerate of s orbital, 2 electrons also in the degenerate of 2s2, 2s orbital rather. You have 3 degenerates in for the p orbital there. Okay, and for 2px has 2 electrons, 2py 1 electron, and 2pz 1 electron. Okay, this should be right because according to the Orn's rule, the electrons are filled into suborbital singly before you start pairing them. So Orn's rule makes this one to be right. So we stop at that. The C will be in our answer. So you can learn about 3 rules in filling electron into orbitals. The first rule is called the Hofbauer principle. The second one is called Orn's rule, while the third one is called Pauli's exclusion principle. Question number 10. Wrought iron is obtained by heating cast iron in a furnace with hematite. That's the answer. So you get. Let us look at the uses of wrought iron. Wrought iron is used to create ornamental and functional pieces such as gates, fences, furniture, and so on.